I'm going to finish up Unit 5, Kinetics. I'm going to cover all the rest of the topics in this unit. I've already covered collision theory or collision model, so really we're going to cover 5.4 and then 5.6 through 5.11. Remember, kinetics is the study of reaction rates. That allows us to determine a rate law, and then we'll be able to come up with a mechanism by which this reaction proceeds. So the first parts that we dealt with in the previous video were looking at what affects reaction rates and how we can write rate laws. Now we're going to look at mechanisms. In your previous videos, we looked at the two types of rate laws: differential rate law, which is just the method of initial rates, and your integrated rate law, which requires a graph. Which type you use depends on the type of data that you're given. If it's concentration versus rate, it's method of initial rates, or what is often called the differential rate law. And if it's a graph, then it's going to be concentration versus time, and that's going to use the integrated rate law and will require a graph to analyze it. So a mechanism is a step-by-step molecular view of how we get from reactants to products, that pathway that occurs by multiple steps. The steps by which a reaction takes place, okay, is what we're really interested in. This is the main reason that we study kinetics, so that we can find whatever step it is that slows that reaction down. So a reaction can only be as fast as its slowest step. No reaction occurs in one step. There might be a few very simple decompositions that might be one step, but most reactions are multiple steps. So whichever step is the slowest controls the rate of that reaction. The slow step is called the rate determining step. So slow step, rate determining step, both mean the same thing. The slow step controls the overall rate and the overall rate law. So it doesn't matter where you are in this traffic scenario, you're not going to go any faster than whoever is up here holding that traffic up. So that slow step controls the overall rate and the overall rate law. Sometimes that rate determining step can be as much as 1,000 times slower than the other steps. So in this funnel analogy, this funnel with the smaller opening is our rate determining step. It doesn't matter how quickly you fill these, this will slow down and control your final reaction. So if we look at a reaction, we do not have a single step where A and B and C all collide together to make this compound. It doesn't work that way. Think back to rolling your marbles in the middle of the hall that day. There was no way we would get three particles to collide and make a product. It has to be a series of very simple steps. So the balanced equation never tells us how reactants become products. It just shows us the final reaction. Reactions occur in a series of simple, effective molecular collisions. Each of the reactions in a mechanism is called an elementary step. An elementary step is a balanced equation that represents an actual collision between particles. So if that's the actual collision between particles, then for that elementary step, we can write a rate law from its molecularity. And molecularity is a term used for the stoichiometry of an elementary step. So an elementary step is going to show simple collisions between particles, and we can write rate laws from those elementary steps, never from the entire reaction, but we can from the elementary step. So molecularity is the number of particles that must collide to form the product. So if we look here, if we just had a reactant decomposing, this would be a unimolecular rate. So that would be our rate law written from this elementary step. These three elementary steps are both bimolecular. You have two particle collisions in all of them. Two A's collide here, an A and a B. Bimolecular and unimolecular are very common. Termolecular means you have three or more particles all colliding at the same time. And statistically, these just do not happen. So most of your mechanisms are written with these simple bi and unimolecular steps. So let's look at how we get the final reaction of ozone decomposing into oxygen. So you're not going to get ozone just splitting apart all at once. It's going to go through two steps. The first step splits off one oxygen, leaving an O2. Then the O3 reacts with this O. Now that's going to be called an intermediate there, leaving you with two O2s, and that gives you the 3O2. So let's look at this.
Gaseous ozone decomposes in two steps. First, one oxygen atom splits off. Next, the single oxygen atom reacts with a second ozone molecule to produce two molecules of O2. The product of the overall reaction is three O2 molecules. Hydrazine is formed in aqueous solution in a three-step process, each step being bimolecular. First, a molecule of ammonia reacts with a hypochlorite ion to form chloramine and a hydroxide ion. Next, the chloramine reacts with a second molecule of ammonia to form a charged species with a nitrogen-nitrogen bond. Finally, the charged species reacts with a hydroxide ion to form hydrazine and water.
So, a series of very simple steps. So if we look at this proposed mechanism, so here is our balanced equation, and it was studied, and it was assumed after studying that species A collided with B to make this intermediate AB. Intermediates are substances that are formed in one step and then used up in the second step. So they're usually a product in one step and then become a reactant in the next step. So AB reacts with another B to form AB2. AB2 is also an intermediate that is formed and used up. Then AB2 and C, these are just simple bimolecular reactions, forms the final AB2C. So when we're looking at a possible mechanism, these steps must add up to the final equation, and all intermediates must cancel out, and they do. Intermediates, again, are species that are formed and then used up in a successive reaction step. Usually the step directly after it, but not always. So as long as they cancel out in the end and are not there, you know they are an intermediate. So the slow step in this mechanism, so we have three steps, and one of these steps is the slowest step, and it would control the entire rate of the reaction. But how do we know which of these is the slow step? Well, with this information, we don't. So we would have to run an experiment. And from that experiment, just like you learned in your last video, You have either the method of initial rates or the integrated rate law that gives you an experimental rate law. So you have to run an experiment for this reaction to figure out the experimental rate law. So if we don't know the rate law, we cannot figure out the slow step. So after running the experiment, we see that for this reaction, it's first order in A, first order in B, and zero order in C. So C has no effect on the rate. A and B are both first order. So now you have to come up here and figure out which of these reactions, if you wrote the rate law, remember only from the reactants. So if you wrote the rate law for all three of these reactions, which one would match this? Well, this would give you A, first order. So if we wrote the rate law from the molecularity, which we can do since it's an elementary step, we would get this. This does match our experimental rate law. These others do not match our experimental rate law, so this must be the slow step. The slow step has to have a rate law written from the reactant's molecularity that matches the experimental rate law. So a mechanism can never be proven, but you may have a possible mechanism if you have two major requirements. First, the sum of the elementary steps must add up to give the overall balanced equation. If they don't add up, so let's go back. If these steps do not add up to give you this equation, then you don't need to look any further. That cannot be a mechanism. So the sum of the elementary steps must give the overall balanced equation. Then the mechanism must agree with your experimentally determined rate law, which you have either found using the integrated rate law or the method of initial rates. Once you know that experimental rate law, then you must match it to the slow steps rate law. So the rate law written from the rate determining elementary step, the slow step, must match that experimentally determined rate law. So let's look at this. We have a balanced equation, and we have run an experiment to get an experimental rate law. We have a proposed mechanism. We have added up our reactions, canceled out our intermediates. This reaction does match our balanced equation. So that's one criteria. So if this is the experimentally determined rate law, what is our slow step? Well, if we wrote the rate law from this equation, this would be first order. There's one of those, and there's one F2. That certainly does match. So this could be your slow step, unless there's some reason why it's not. The second step can't be. There's no reason why this cannot be. All the other criteria are met. So this is your slow step. The rate law from the slow step matches the experimental rate law. So let's look at one more. We have a final equation that's balanced. We have an experimental rate law. We have a proposed mechanism. And notice our intermediates would cancel, leaving us with A plus B, D, and G. So this does match the final equation. So they have given us this as our slow step. So they're asking us if this is a possible mechanism. If we wrote the rate law from this step, we would have that rate law. That rate law from the slow step does not appear to match the experimental rate law. So we may be tempted to say, no, this is not a possible mechanism, but we need to look a little further. First of all, in this rate law that we've written, we have included an intermediate, and an intermediate can never be in the final rate law because it's not a reactant and it's not a product. So it can't be in our rate determining step. Your rate determining step can only have reactants in it. So if we look further, it appears that this does not match, but it does. And the only way it does is because the intermediate C is formed in a fast equilibrium step. So if we look at C and where it was formed before the slow step, we see that it was formed in a fast equilibrium step. That means that C can be substituted with A and B. They are in an equilibrium with each other. That's called a steady state approximation. So we can substitute in A and B for C. If we do that, we see A first order, B first order, and D first order, and that does match our experimental rate law. So C is an intermediate. It cannot be in the final rate law. Intermediates can never be in the final rate law. The final rate law has to include only reactants. If C was formed in the step prior to it being in the slow step, and it is formed in a fast equilibrium step, then we can substitute in for C with A and B. So A and B are substituted in, D still remains, and based on our substitution, this being substituted with that, we have a rate law that matches our experimental rate law. It is a possible mechanism, but you can only do this kind of fast substitution if you have a fast equilibrium step. So if you have a mechanism that includes an intermediate, if you cannot substitute out that intermediate, then it is not a possible mechanism. But if you can substitute out that intermediate, and you can write a rate law that matches, then it is a possible mechanism. So the steady state approximation allows us to substitute in A and B first order for C. There is an activation energy for every step in a mechanism. We're used to writing the exo or endothermic reactions for the whole reaction. We don't think about the fact that there are elementary steps. Okay? So if you are looking at a mechanism, you must have the activation energy for all of those steps. The total activation energy controls the rate. So that slow step in that mechanism still is going to control that total reaction. So it's going to have the highest activation energy. So here you can see you have a three-step mechanism, This first activation energy is short. It's not very much energy required to get over that first energy barrier, so that's probably a fast step. The second step is much larger, So this is the highest activation energy. So this is the slow step in the mechanism. And this is another fast step. So this is your rate determining step. These are your intermediates. These are things that are formed and then used up. Formed in this reaction and used up as you go to the next one. These are your three activated complexes. Activated complexes are not intermediates. You're never going to see activated complexes in a mechanism, only intermediates. So catalysts are going to take that slow step and somehow alter the mechanism so that it requires less energy. So catalysts allow reactions to proceed by a different mechanism, a new pathway that has a lower activation energy. More molecules will then have this lower activation energy and the reaction will go faster. It will not change your delta H. From here to here will not change. What you're changing is this energy barrier right here. So you're coming up with a mechanism that has a lower activation energy. So it's going to start at the same place and end. This really should be right overlapping that. But the energy required to get there is much less. So there's your catalyzed reaction and your stop right there, your non-catalyzed reaction right above it. Okay? So make sure you realize that you do not affect your final delta H. You're not affecting the heat or the thermodynamics, you're only affecting the rate. And you're only affecting that energy barrier by lowering that activation energy. So you have homogeneous catalysts, which occur in the same phase, all liquids. Or you have heterogeneous catalysts, which are solid states. Usually you have liquids with solids or something along that line. So your homogeneous catalysts would be things that would form these intermediate molecules that would help collisions to take place and allow your reaction to occur. Your most common are acid-base catalysts, and these usually use a proton or remove a proton to change one structure into the other. So acid-base catalysts or enzyme catalysts, which you've learned in biology. So you have a molecule with active sites, so your substrate or your molecule of interest can come in and then interact and be broken apart. These are both still homogeneous catalysts. For chemists, the acid base is very common, and for biology, it's the enzyme. But enzymes, of course, are catalysts. The surface catalyst, sort of like your catalytic converter, has a platinum surface, or it could be gold or silver. It's a very pure metal surface where substances come down on that surface and then interact, break apart, and leave.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface.
When you have a heterogeneous catalyst like that, your rate increases until all of your active sites on the solid are filled up, and then the rate remains constant. You used the colorimeter again in kinetics to measure the rate of a reaction of a dye fading. So you were
Take absorbance measure.
Let's go back a minute before I play that video. You were able to measure the rate by watching the absorbance change of the colored dye. And then, since absorbance is directly related to concentration of color, you were able to come up with a rate law.
Take absorbance measurements starting at 400 nanometers and then at 20 nanometer increments. When the absorbance begins to increase, reduce the increment between readings to 2 to 5 nanometers. After the absorbance peaks, once the reading stabilizes, return to 20 nanometer increments. Draw a smooth curve through the data points. Lambda max is the wavelength at the top of the curve.
Lambda max is the optimal wavelength for studying your substance. So most experiments at your level give you what that wavelength is. Of course, we know that we're absorbing that complementary color of light. So here is the lambda max for this substance, right here in this nice yellow wavelength, and this was our crystal violet, and it was a violet colored dye, so we would expect it to absorb in the yellow wavelength. You can get absorbance outside of here, but you're not going to get a very good reading, and you've seen that in several of your questions about spectrophotometers or colorimeters. So we took the crystal violet dye, we added sodium hydroxide, and we very quickly, after we mixed these, we put it in the cuvette and started measuring the fading of the color as we watched the line on the graph decrease. It fades very quickly, so you had to transfer it quickly. As the dye faded from a pale purple to colorless, you got a line. You then, since absorbance is directly related to concentration, you looked to see whether that line was a straight line with the natural log, or whether it was a straight line with concentration, or whether it was a straight line with inverse of concentration, and that gave you your order. I believe this was first order with respect to crystal violet. At least that's what this example data shows. So using your colorimeter to measure concentration, to measure change in concentration, which is a rate, we've used it for both of those experiments, and we have used it, and we'll talk about it, with equilibrium.